All right, we're live. Hello to whoever's here. It only looks like there's a few of us. That's fine. Um, yeah, so the plan, I guess, for today is to just do any of the questions from the study guide that you want to do. Yeah, so just put in the comments what questions you want to work on, and then we could go from there. I don't have any coffee, but I do have water, so I guess we could do a simultaneous sip if anybody wants to. Got my Wake Forest cup. Not as good as coffee, but it's okay. All right. So just put in the comments, and I have the questions on my iPad, so I can look them up. Could we do question 5 about eigenvalues? Yes. Is that the true or false, or just question? Well, I'll take a look. Oh, the proof one. Yeah, let's do this. Okay, so it says show that x is an eigenvector. This is the one, right, Maddie? Okay, so if we have x is an eigenvector of the matrix AB, and bx is not equal to 0, that's kind of more of a formality, then bx is an eigenvector of the matrix BA. Okay, so basically what we want to show that, all right, so b times x is just a vector. Okay, so what we want to show is if we take this vector here and multiply it to BA, then we get some scalar multiple of BX. So we want to show that if we take the matrix BA and we multiply it to the vector BX, it's some multiple, which we'll call, let's say, lambda 0 times the vector. Okay, so that's our goal. If we could show this, we're done, right? Because that's what it means to be an eigenvector. It means that if you multiply by the matrix, you get a scalar multiple of the vector. So far, so good. I'll give a second for people to put any comments or concerns in the or questions, I guess, in the chat. But this is our goal. We want to show this. Okay, so I don't know if you have any questions or not, but I'm going to keep going. So let's just start with what we were told. X is an eigenvector of the matrix AB. Apply it to X, you get some scalar multiple of X. Right, that's what it means to be an eigenvector. Okay, well, this is a matrix times a matrix times a matrix times a vector. We have properties of matrix multiplication that says we don't really need these parentheses. It doesn't matter which order we do this. Okay, so this is really equal to the matrix B times A times B times X. All right, all I did was just remove the parentheses. And now look. What is this? A times B times X? Well, that's lambda X. Right, so this is equal to B times lambda X. Where lambda is just some scalar. We have another property of matrix and scalar and vector multiplication that we could move the scalar out in front of the equation. So we're left with lambda times bx as we desired. Scalar multiple of bx. Thus, bx is an eigenvector for ba. So that's the proof. So are there any questions about why that's true? Or just thoughts? Feel free to put them in the chat. And if there's no thoughts or questions, feel free to just ask for the next example you want to go over. Yeah, no, a good strategy is try to figure out, we want to conclude that bx is an eigenvector of the matrix BA. So write in math terms, what does that mean? And then see if we can get there from what we were given. That's kind of the technique we use. Right? We don't really, in a linear algebra class, we don't really have too many proof techniques we could use. So usually they're pretty straightforward. Can we go over true or false of eigenvalues? Yeah, Shutong, which ones do you have a specific? Or all of them? I don't really want to go through every single one of them, but are there? Okay. Yeah, but I'm not going to. I'm not going to write it out. I'm going to just speak it. If there's one in particular you want me to write out, I'll speak it and give an explanation. Okay. Just because I want to do some of the longer examples. Okay. If A is invertible and 1 is an eigenvalue for A, then 1 is also an eigenvalue for A inverse. I guess we could probably write some of these out. Yeah, so this first one's good because it kind of makes us check that we know what it means to be an eigenvalue. Okay, so we have A is invertible and 1 is an eigenvalue for A. That means that there's some vector, which we could call X, or I think I called it V in the answer key. So So 1 is an eigenvalue for A means there's a vector, which we could call X, such that AX is equal to 1 times X. Okay, and we want to show there's a vector, maybe call it y, such that A inverse y is equal to y, right? That's what it means for one to be an eigenvalue of A inverse. AX equals x, and just multiply on the left by A inverse. Right, so we have A inverse AX is equal to A inverse x, and so x is equal to A inverse x. Right, so multiplying by A inverse on the left of x gives us 1 times x. So hence we have 1 as an eigenvalue. Okay, the ones that I have that are false and I provide a counterexample, those are kind of tough to explain unless you just look at the counterexample. Right, the next one says if A is row equivalent to the identity, then A is diagonalizable. Basically, just find a matrix that's just basically a good idea for the ones that are false is just like come up with an example on your own and see if it works out as a counterexample. And more often than not in this class, it will work out as a counterexample. Okay, and we really can't do all. There's all the way up to t of these. Okay, I'm going to just pick some random ones. Each eigenvector of A is also an eigenvector of A inverse. Let's see if that's true. Or of A squared, sorry. All right, so let's see if this is true or false. Each eigenvector of A is also an eigenvector of A squared. Well, let's just, if we have an eigenvector of A, that means AX equals lambda x. And now let's see what happens if we multiply x to A squared. So A squared x is equal to A times AX. This is equal to lambda x, which is equal to lambda AX. And again, AX is equal to lambda x. So this is equal to lambda squared AX. Oop. Lambda squared x. So yes, each eigenvalue A is an eigenvector of A. Each eigenvector of A is an eigenvector of A squared. And notice that its eigenvalue gets squared when we square A. And that's not a coincidence. Okay, let's look at a couple other ones. Tomorrow, depending on the time. After this, can you explain 6 on page 5? Yep. All right, I'll just pick a random one. Okay, how about this one? Similar matrices always have the same eigenvalues. Okay, so what does it mean for matrices to be similar? A is similar to B means that A equals P, B, P inverse for some matrix P. Similar matrices, so we have A and B, and we want to show that A and B have the same eigenvalues. So let's say so suppose we have that lambda is an eigenvalue of A. We want to show that it's also an eigenvalue of B. Okay, and so if lambda is an eigenvalue, that means there's a vector such that AX equals lambda X. But A we said was the same thing as P inverse. And then we can multiply on the left by P inverse. And we have that B P inverse X is equal to lambda times P inverse X. And this shows that it's an eigenvector. I mean, an eigenvalue, right? B times this vector is equal to lambda times the same vector. So they have the same eigenvalues, but different eigenvectors. But the question just asks if they have the same eigenvalues. So yes, they have the same eigenvalues. But we didn't show that they have this doesn't tell us if they have the same eigenvectors or not. Yeah, okay. What would you have to know? 20 variables in order to know that every associated non-homogeneous equation has a solution? Is our matrix A is, well, let me check again. We have 18 equations. So there's 18 rows and there's 20 columns because there's 18 rows and 20 columns. And so basically the question is, how do we guarantee that AX equals B always has a solution. Right, that's really what the question is asking. How do we guarantee that AX vectors B? So does anybody have any ideas? Another way to word this. Well, we can't have a pivot in every row and column, right? Because it's an 18 by 20 matrix. So we could have at most 18 pivots. But yeah, we need a pivot in every row, right? We would need, so those aren't the numbers 0, that's like pivot boxes. We would need a pivot in every row, and that guarantees that AX gets mapped onto R18. So this is another way to write this is we want the map that sends X to AX to map onto R18. 18 comes from the number of rows here. And so basically what this is saying is we need a pivot in every row. All right, so just you could look back in your notes about what it means to be onto, or what were the conditions that needed to be satisfied to be onto, but basically it just means we need a pivot in every row. Does that make sense? I'm glad you were able to make it for the office hours, James. We have a test tomorrow at 9:50. In 1A on page 5, yeah, let's do that. Okay, so the statement is the set of all, oh, sorry, 1F. Okay, good. That, yeah, 1A is just something we showed in class. It's basically showing that the span was a vector space. Yeah, but 1F says the non-pivot columns of a matrix are always linearly dependent. Yeah, 1A is easy. Smiley face. Okay, so the non-pivot columns of a matrix are always linearly dependent. Okay, so this, So let's just try to craft up a counterexample. Right? So like for instance here, like the reason why I suspect that it's not true. Does it say dependent or independent? Yeah, always. Yeah, why you should, I mean, either way it's false, but why you should suspect it's not true is like, look at this example here. Our matrix A had two non-pivot columns, and at least I have convinced myself that this is probably false. We should try to craft up a counterexample to just show it's false. So, yeah, the counterexample I provided, if I could find it, oh, whatever. I don't know where it is, but basically we just need to come up with a matrix who has linearly independent non-pivot columns. Okay, so for instance, if we had a matrix like 1, 0, 1, 0, 1, 0, this would have linearly dependent pivot columns, right? I mean, non-pivot columns, right? These are the same vectors, so it's clearly linearly dependent. But we can change our matrix, right? We just have to come up with one counterexample. So let's just shave off a column to solve our problem. So here we have our non-pivot column is just one vector, and one vector is always linearly independent unless there's, unless it's a zero vector. If you're not happy with this counterexample, you wanted something a little bit more complicated, we could just, and again, look at the non-pivot columns, and you could check that that is clearly a linearly independent set. Okay, so the question was referring to the non-pivot columns alone. Yeah, isn't that what it's? Yeah, just the non-pivot. So if you take a matrix and just ignore all of the pivot columns and treat each of those columns as vectors, because of a non-pivot column is dependent on the pivot column, right? That sound, yes, yeah, and that's from the, yeah, that's true. That's kind of like that kind of is the reason why the pivot columns make up a basis for the column space. Is like the non-pivot columns don't really contribute anything. The pivot columns kind of capture it all. That's a good question. No problem. Anything else? We could even do questions from the book if you happen to have those you want to go over. Questions from class. Okay, well, while you guys think of a question you want to ask, I'm going to tell you a story, and you have to decide if it's funny or not. Okay, question was asked, no story. Will the exam go all the way through the lesson we had today? Yes, it's going to cover from 3.1 all the way through 5.5. It will be the 5.5 question will be relatively straightforward. So just make sure you know how to do basic the basic examples that we're doing today and yesterday. Today and tomorrow. Sorry. All right, so I'm going to tell the story while you guys come up with questions. I was on Twitch the other day because I saw somebody on Reddit posted that they were, there'll be a stream tomorrow, James. 9 o'clock and 10 o'clock for calculus. Somebody posted on Reddit saying they were having live math office hours. So I wanted to see what they would be like, just to get some inspiration. And so I hit the link, and I see I was the only viewer. It's like, this is odd. And the guy's working on his homework, Calc 3, and he has no clue how to do it. So I just did his homework for him while he was on Twitch. It was really cool. And then I went to bed because it was late. But yeah, that's what's happening to me during this social isolation thing. I've been doing random people's math homework on Twitch. That's sad. Only one viewer. Yeah, it was me. Okay, are there any other questions? Oh, Noah, I taught him. Let me tell you, I kind of held his hand through it. I said, because he was screen sharing his textbook. So I was like, "Are you sure you are doing this correctly? You should check this definition." If you've taken Calc 3, what he was working on was like local max, local min, and saddle points, and so it's just like following an algorithm, but you got to do it. Oh, those are easy. Yeah, that's what I was thinking, Noah. Did I invite him to my stream? No, I didn't want to. I didn't want to embarrass him during his office hours he was having on Twitch. That's like the easiest part of Calc 3. Yeah. Directional derivatives too. Well, that is, yeah, partial derivatives. Okay, are there any other? I mean, I could have this delayed conversation with Noah live on YouTube if we want to continue this, but I would rather, no offense, Noah, I would rather do some linear algebra questions. None taken. All right, I'll give about another minute or so for a question to trickle in. Five viewers and no like button smashed. What a shame. Not even from my own brother. Oh, yeah. Okay. So you guys are alive. All right. Well, can you at least give me some feedback that you say that I'm good to go? Like no questions or just find something. Good stream. See you tomorrow. Yep. Have a good one. See you tomorrow. That's all my questions. Thank you. Yeah, so I guess this is probably a good place to wrap up if we're good with that. Tomorrow, the plan is we have like 2 examples left for complex eigenvectors, and then we'll have time to ask more questions. So try to, just come up with any questions you want to talk about tomorrow, and then I'm sure you guys will do great on this test. You guys spent 40 minutes with me during this live stream today. I mean, that's pretty good. Okay, well, see you in the morning. Be careful. Wear a face mask if you go out in public. That's my new thing. Do what we got to do. Hopefully we can be back in the fall. Okay, see you tomorrow. Bye-bye.